nanoHUB-U, online instruction.
Hey everyone, welcome to lecture 1.2. So in the last introductory unit, we just talked about the basic problem of band structures, okay? And then we also said that you could have periodic wells of quantum particles. And then the question is, how do they interact with each other? But before we go into the solution, let me also mention explicitly that the same kind of problem actually occurs in optics. So much like electrons getting stuck in wells, we could also have photons getting stuck in high dielectric materials. So if we had a stack of high and low alternating dielectric materials, this is called a distributed Bragg reflector, then you can imagine that, of course, it's periodic if you have many layers. And then the question is, like, what would be the boundary conditions, and would each photon actually get stuck in a high index region, kind of like internal guiding of light. So it's not necessarily obvious, but Felix Bloch actually thought about this problem for a long time. And then he said he didn't understand at first, like, how could the electron sneak by all the ions in a metal, but he performed some analysis, which he called straight Fourier analysis, of course, based on Fourier series. And then he found, to his delight, that the wave that would result from this sort of problem only differs from the plane wave of free electron by periodic modulation. And so now we need to unpack what does that mean exactly. So that means that the solution in the periodic potential has to be a product of two terms. First, we have a periodic function with the same period as the periodic structure itself, and then we have a plane wave. So then that means we can write down all our solution in this form. So our wave function psi would be a, so that's arbitrary constant, times e to the ikx times u of x. And we can assume that u of x plus a, where a is the periodicity, is equal to the original u of x. So this is different from what we might have guessed, which was just that the whole solution is u of x. But we have to add this plane wave as well, because although k could be 0, and then basically give us a solution like u of x, there could also be a non-zero k, which is also a reasonable solution. So that's very important. And then the question, of course, becomes, like, how do we start to solve the Schrödinger equation using this Bloch solution, right? So then we write down the Hamiltonian times the Bloch solution is equal to the energy at a given k times the Bloch solution. But then the question is, what kind of basis should we use for this periodic function? So of course we can guess one thing, which is real space. And then we basically break up real space into different grid points. Okay, so we could grid it and then try to solve it. Of course, once we've done that, we can actually pull out the plane wave that's associated with the h bar squared k squared over 2m. And that actually is subtracted from this e of k on the right-hand side. Now, there's a problem, of course, with this system, which is that it's not positive definite. So that makes it very hard to solve numerically with a lot of popular tools. So in other words, you can imagine that some of the eigenvalues that you obtain from the system will be negative values. So it can cause problems. It's not bounded from below. You can get arbitrarily negative values. So instead of trying to solve it in this basis directly, we need to think of something else. And so in the next lecture, we'll actually talk about that.